Hello, this is Matt Dean with A Plus College Ready, and today we're going to work some motion in 2 dimensions practice problems. We'll start out here with practice problem 1. It says Hayden walks 12 meters due north, then 8 meters due south, then 14 meters due west, and finally 18 meters due east. What distance does he travel? So remember that we might notate distance as a delta S. You might just see it notated as D. But the important thing to remember about distance is that distance is a scalar quantity. The magnitude of the distance matters. The direction does not. So if we want to calculate the distance traveled, we simply need to add up all the distances in each segment of this trip. So Hayden travels 12 meters, 8 meters, 14 meters, and 18 meters. The distance he travels those distances in doesn't matter. So we simply add those up, 18 plus 14 plus 8 plus 20, and we end up with a total distance traveled, or delta S, of about 52 meters. In problem 2, we have a very similar problem to problem 1, except this time we're being asked to find displacement. Displacement is a vector quantity. In vector quantities, both the magnitude and the direction matter. So if we want to find something's displacement, we're comparing where, in this case, Hayden started at and where he finished at. And the displacement is going to be a straight line between those 2 points, the start point and the finish point. So to calculate displacement, we're going to need to, first of all, combine together movements that are in the same plane. So for example, 12 north and 8 south are in the same plane. We're going to think of north as positive and south as negative. So in this case we have 12 north minus 8 south. So we end up with a net north-south displacement of 4 to the north. Alright, we can also combine the 14 meters west and the 18 meters due east. We'll think of east being positive to the right and west being negative. So when we combine those two together, we end up with positive 4, or 4 newtons to the east. So we have 4 newtons north and 4 newtons east, or 4 meters, 4 meters, not newtons. And we need to combine those together. Well, the only good way, or there's several ways you can do it, but the best way to combine vector quantities that are not in the same plane together is to use what's called the tip-to-tail method of vector addition. And the way we want to do that is we want to draw in one of the vectors. Let's start with the 4 meters east. Draw that in as a vector. We're going to go to the tip of that vector, and we're going to start with the tail of the second vector, which is 4 meters north, like so. We're now going to draw in what's called the resultant. The resultant is the line that represents the sum. And that resultant runs from the tip, or the tail rather, of the first vector in a straight line to the tip of the second vector. That is r. And we're going to solve for r using the Pythagorean theorem. So we're going to say r squared, the hypotenuse of our triangle, equals to 4 squared plus 4 squared. Solve that out for r, and when we do, we take the square root of what's going to end up being 32 here, and we're going to end up with a resultant that's equal to 5.66. In this case, 5.66 meters. But what we've got to remember is that vectors have both a magnitude and a direction. We've got to indicate the direction here as well. And there's several ways you can find the direction, but let's talk about the easiest way and probably the most commonly used way. Before we do that, let me make a little space with my eraser. Alright, so typically you're going to give direction in terms of the angle. And the most common way of doing it is to give it in terms of the smallest angle between the resultant and the horizontal. So here's our horizontal, and we want the smallest angle right here between our resultant and that horizontal. So we need to solve for this angle. We're going to have to use trig functions to do that. We're dealing with right triangles. And the easiest way is to use the tangent. So remember the tangent function. We'll call our angle here angle of theta. So the tangent of theta is equal to opposite, which is this side, 4, over adjacent, which is this side, also 4. So we have the tangent of theta is equal to 1. We're going to take the inverse tangent of both sides, and what we end up with is a 45-degree angle. So what we're going to get for an answer is 5.66 meters. That's our magnitude, and our direction is going to be 45 degrees. We'll say 45.0 degrees to get our sig figs right. We also need to give it in terms of north, south, east, and west. And the easiest way to do that is to start at the horizontal, in this case the east, and we're moving toward the north to get to this resultant line. So we're going to say this is 45 degrees north of east. So the correct answer here is answer B, 5.66 meters at 45 degrees north of east. All right, now we're going to look at problem number 3. This says Ethan throws a 5-kilogram ball horizontally from the edge of a 90-meter tall cliff with an initial velocity of 40 meters per second to the right. How long does it take the ball to reach the ground? What we've got to think about here is that we're throwing it off the cliff. Starts off moving horizontally. We know there's no horizontal forces. We're going to ignore drag just like we normally would. But there is a force acting vertically, and that force is gravity. So what's going to end up happening is the horizontal speed of this object isn't going to change. But the vertical speed, the vertical velocity is going to accelerate at the rate of gravity, negative 9.81 meters per second square. So the path or the trajectory that this ball is going to follow is going to be sort of a parabola. So here's what we've got to do. The time that it takes for this thing to fall to the ground is completely determined by the vertical velocity because it's falling vertically. In most of these projectile problems, we need to keep the horizontal motion separate from the vertical motion. So let's think about what we know. And let's, again, just think about vertical quantities here for a second. So we'll say vertical quantities. Our initial vertical velocity, we'll call that v sub 0, is 0. The thing starts off with only a horizontal velocity. Our acceleration is negative 9.81 meters per second square. Also, we're going to call it delta y. That's our vertical, displacement. The thing has to fall 90 meters to get to the ground. So we're going to say the vertical displacement is negative 90. All right, so what we want to do now is we want to find a time somehow. And there's several ways we can do it. The easiest way to solve for time is going to be to use this kinematic equation. Delta y equals VOT plus 1/2 AT squared. And if we come down to the bottom and plug in what we know, that's going to end up giving us this. So our delta y was negative 90 meters. I'm going to leave off the sig figs just to save some space here. Negative 90 equals, well, our V0, our vertical velocity, our initial vertical velocity was 0. So the VOT component just becomes 0 plus 1/2 times the acceleration, which is negative 9.81. And again, that's meters per second squared times t squared. So now we're going to solve for t. And when we solve this out for t, we end up with a time of 4.29 seconds. So that is the total amount of time in the air, 4.29 seconds. So our answer is answer C. All right, now let's continue on with problem number 4. And what we need to keep in mind is that problem 4 is the same problem as problem 3, except this time we're being asked for the range or the horizontal displacement of this ball. we need to remember from the last problem that the total time in the air was 4.29 seconds. So we're going to say t equals 4.29 seconds. In this problem, we're being asked to find the range, the horizontal displacement. The range is completely dependent on the horizontal velocity. And remember that the horizontal velocity in most projectile problems doesn't change because there aren't any net horizontal forces acting on the ball. So our horizontal velocity is uniform, it's constant, and it is 40 meters per second for the entire trip. Typically, when we're dealing with constant velocity style problems, we can use this equation, delta x equals vt, to solve for displacement. So our range, delta x in this case, is going to be equal to the horizontal velocity, 40 meters per second, times the time in the air, which was 4.29 seconds. Solve for delta x, and we end up with a range or horizontal displacement of about 172 meters in this case. So we're looking at answer A as the correct answer. Alright, so now we're ready to look at problem number 5. And again, it's pretty much the same problem as the last two problems. All the basic information is the same. We probably need to remember that our total time in the air was 4.29 seconds. This time we want to know what's the ball's vertical velocity at the instant before it touches the ground. So it's asking us essentially to find the final vertical velocity. Again, that's completely dependent on other vertical quantities. Remember that vertically we know that the initial vertical velocity is 0. We know the acceleration vertically is negative 9.81. And we know the displacement vertically is negative 90 meters. We're trying to find the final vertical velocity. The easiest way to do that is to use the kinematic equation. V, final velocity, equals V0, initial velocity, plus A times T. So in this case, V is what we're looking for, final velocity. Our initial vertical velocity was 0, plus our acceleration, 9.81, negative 9.81. Remember, the negative here just means it's in the downward direction, meters per second square. And we want to multiply that by t, our time in the air, 4.29 seconds. Problem 6, again, we're looking at essentially the same problem, but this time we want to know what are the vertical and horizontal components of the ball's velocity at t equals 2 seconds. So 2 seconds after the ball is thrown, we want to know what's the vertical component of the velocity. We also want to know what's the horizontal component of the velocity. There's some key things to remember here. First of all, we should remember that the horizontal component typically doesn't change during a projectile problem. It's uniform, it's constant. So our horizontal component is going to be 40 meters per second, positive 40, because it's to the right, for the entire trajectory. For the vertical velocity, we know that the vertical velocity is constantly changing, and it's constantly changing due to the acceleration due to gravity. So we need to calculate what's the vertical velocity going to be after 2 seconds. Remembering that we start off with an initial vertical velocity of 0, an acceleration of negative 9.81. Again, that's meters per second square. And in this case, we've got a time of 2 seconds. The easiest way to calculate the vertical velocity after 2 seconds is to use the kinematic equation, V equals V0 plus AT. So V is our final velocity. That's equal to our initial velocity, 0, plus the acceleration, times the time, 2 seconds. We calculate that out, and we get a vertical velocity at 2 seconds of negative 19.6, and that's meters per second. So this is our vertical component, and positive 40 meters per second is our horizontal component. So we're looking, the correct answer on problem number 6 is C. All right, now we're on problem 7. And again, we're looking at essentially the same problem. But this time we want to know what's the resultant velocity of the ball at t equals 2 seconds. Well, in problem 6, we found that at 2 seconds, the vertical component of the velocity was negative 19.6 meters per second. So I'm going to call that Vy in this case, letting us know that that's the vertical component, negative 19.6. Again, meters per second. And the horizontal component of that velocity was positive 40. Well, the resultant is the sum of all the different components. So to find the resultant velocity, we need to add together these two vectors. Now, since they're in different dimensions, we can't just say 40 plus negative 19.6. To add vectors in different dimensions, you have to use the tip-to-tail method of vector addition. To do that, we're going to first draw in our 40 meter per second horizontal component, just label it as 40. We're then going to draw in our vertical component, which is downward in this case. And I'm just going to write 19.6 because the direction of our arrow is what the negative means. We're going to draw in our resultant from the tail of the first vector to the tip of the second vector, like so. And we're going to solve for this resultant using the Pythagorean theorem. So we're going to say r squared equals 40 squared plus 19.6 squared. All right, we solve that out, and we're going to end up with a resultant magnitude of 44.5 meters per second. But again, this 44.5, that's just our resultant magnitude. Velocity is a vector. We need a direction. And remember, the most common way to express that direction is to find the smallest angle between your resultant, this line, and your horizontal, this line. So this is the angle that we're going to be looking for. And the easiest way to find that angle, which we'll call theta, is to use tangent. So we're going to say the tangent of theta equals to the opposite side, 19.6, divided by the adjacent side, which in this case is 40. We're going to take the inverse tangent of both sides, and we end up with an angle of 26.1 degrees. Now in this case, our vector is not traveling north, south, east, west necessarily. So the way we're going to express this angle is we're going to say that our answer is 44.5 meters per second at 26.1 degrees. And notice that that resultant is traveling to the right and also below the horizontal. So our correct answer here is C. 44.5 meters per second, 26.1 degrees, and that is below the horizontal and to the right. All right, so now we're going to look at problem number 8. And in this case, Justin wants to cross a 925 meter wide river. His boat's velocity is 28 meters per second due east across the river with respect to the water. That means if the water wasn't moving at all, Justin would go straight across the river at a speed of 28 meters per second. But in this case, the water is moving, and the water in the river flows due south at a rate of 6 meters per second. If Justin keeps the boat pointed directly at the opposite bank, meaning he doesn't angle it or anything, for the entire trip, how long does it take him to cross the river? The important thing to realize here is, just like we did in the last couple of problems, we need to think of the vertical motions and the horizontal motions separately. So we have this river, and the distance across this river is 925 meters. Justin is moving in this direction at a speed of 28.5 meters per second. That speed is unaffected by the flow of the river. So if we want to calculate his time across the river, we're going to go to one of our most basic equations, which is delta x equals vt That speed of 28.5 meters per second is constant across the river. We're going to solve that for t. So that's going to give us t equals delta x over v. We're going to plug in some numbers. Our delta x in this case is the distance across the river, 925. And we're going to divide that by the speed across the river, 28.5. And again, that's in meters per second. May run out of room here. Do the math on that, and we end up with t equals 33 seconds. So that's the time it takes him to go across the river. Answer A is the correct answer. Now realize though, he's not going to end up, if he starts here, he's not going to end up straight across over here. Because in addition to his motion pushing him across the river, the movement of the water is pushing him down the river. So he is going to cross the river in 33 seconds. But when he gets across, instead of ending up somewhere in here, he's going to end up somewhere down here. All right, so here's problem 9. Again, same problem, but in this case we want to know what is his resultant velocity with respect to the riverbank. So to get a resultant velocity, we need to add together all of the vectors that are making Justin move. So in this case, he has a horizontal velocity of 28 meters per second straight across the river. And in addition to that horizontal velocity, he's also being pushed down the river at 6 meters per second. So we're going to add together those two vectors using the tip-to-tail method of vector addition. We're going to draw in our resultant from the tail of our first vector to the tip of our second vector. And we're going to solve for r using the Pythagorean theorem. So r squared is going to equal 28.6 squared plus 6 squared. We're going to solve that out for r. And when we do, r is going to equal 28.6. Now some of you are going to fall the trap here, and you might choose C. Remember though that velocity is a vector, and we've got to give a magnitude, which is what the 28.6 is, but we also have to give a direction, and we want to give that direction in terms of the smallest angle between our horizontal and our resultant. So that being said, this is the angle that we want to find. We'll call this theta, and we're going to solve for it using tangent. So we're going to say the tangent of theta equals opposite this side 6 over adjacent this side 28.6. We're going to take the inverse tangent, and we're going to get an angle of 12.1 degrees. And we're going to express that. We're going to say start at the east and move toward the south. So start here, move here. So we're going to say 28.6 meters per second, 12.1 degrees south of east. And that puts us with the correct answer of B on problem number 9. All right, problem 10 again is essentially the same problem, but this time we want to know how far south, how far downstream Justin's going to end up after he crosses the river. And what we've got to know is that southward movement is completely dependent on the southward velocity. The southward velocity in this case is a constant 6 meters per second. So to calculate the southward displacement, which is what we're looking for here, we're going to use, in this case, delta y, we'll call it since it's kind of vertical, is equal to vt. The velocity in the south direction is 6. And the time that it took to cross the river from the previous problem was 33 seconds. So delta y, in this case our displacement down the river, 6 times 33 is equal to 198 meters. And we might want to say to the south, but 198 meters. Answer A, correct answer on problem 10. All right, so now we're ready to look at problem number 11. Problem number 11 says Russ fires a cannonball with an initial velocity of v at an angle theta above the ground, horizontal, and to the right. Which of the expressions below best represents the maximum vertical height reached by the cannonball? First thing we need to do in this case is to think about the components of this velocity v. Alright, so what we want to do in this case is we want to draw in that velocity. So this is v, and it's at an angle of theta. We want to resolve this velocity into components. So we're going to draw down a vertical right here. I'm going to call this vy, the vertical component, and I'm going to call this one vx, the horizontal component. Solve out for both. So I could say that the cosine of theta is equal to the adjacent side, vx, over the hypotenuse, v, and I could rewrite that as vx equals v cosine theta. Well, I could do the same thing for sine, so I could say sine theta is equal to opposite vy over hypotenuse v. So vy is equal to v sine theta. Alright, so in this case I'm trying to find the maximum vertical velocity, the maximum vertical height rather. Remember that vertical motion is dependent on vertical velocities, vertical displacements. So I can forget about the horizontal part of this problem right now, and let's just think about vertical quantities. So my initial vertical velocity is equal to the vertical component of the original velocity, v sine theta. At the maximum height, so the ball is going to go up, 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 up. It's going to get to some maximum height. At that instant in time, its vertical velocity is 0. It still has a horizontal velocity. The horizontal velocity is constant for the whole trajectory. But at this instant in time, its vertical velocity is 0. That's at the max height. So here's what we know. At the maximum height, the final vertical velocity at that point is 0. The initial vertical velocity is v sine theta. The acceleration between those 2 points is the acceleration due to gravity. And I think that's enough to help us work this problem out. We're trying to find that maximum height. The kinematic equation we're going to use is delta, let's use this one. Let's say that v squared, final velocity squared, equals initial velocity squared plus 2a times the displacement, delta y. We're going to solve that for delta y. So we needed to subtract VO from both sides. Well, before we do that though, let's remember that the couple things here. Remember that the final velocity at the maximum height is 0, so this part's going to be 0. Also remember that VO is our initial vertical speed, which is v sine theta. We're going to square that, plus 2 times the acceleration, which is acceleration due to gravity, times delta y. Now we want to solve that for delta y, and when we do the math, solve for delta y, that ends up giving us answer A. Delta y equals negative v sine theta squared divided by 2 times negative 9.81 meters per second square. Alright, so here we have another problem, another projectile problem. Here we have the green arrow firing an arrow at 60 meters per second, so let's draw that in like so, at a 40-degree angle above the horizontal and to the right. This angle is 40 degrees. We want to know how much time does it take the arrow to return to its original launch height. So our arrow is going to follow a parabolic path, and we want to know how much time does it take it to go from right here all the way back down to that same height over there. Couple things to think about. The time in the air is determined by vertical motion. So let's think about what we know vertically. Our vertical displacement, we'll call it delta y in this case, is 0 because we're starting vertically at the same place we're ending. Our initial vertical velocity, v0, is not 60. It's going to be the vertical component of that 60. So let's draw down a 90 here and let's find the vertical component, this component, Vy. So let's say sine 40 equals opposite Vy over hypotenuse, 60. Let's solve that for Vy. So Vy is going to equal to the sine of 40 times 60. And when we calculate that, the sine of 40 times 60, we end up with about 38.6. So that 38.6 is going to be our initial vertical velocity. And that's in upward direction. Hopefully you've also learned by now that when a projectile returns to the ground, if it returns to the same height that it left from, its initial vertical speed is going to be the same as its final vertical speed. They're just going to be going opposite directions. So in this case, our final vertical velocity is going to be negative 38.6. Same speed, opposite direction. And the acceleration between those two is just the acceleration due to gravity. So the easiest way to solve for time is going to be to use this kinematic equation. V equals V0 plus AT, which in this case is going to be negative 38.6 equals 38.6, the initial velocity, plus the acceleration times the time. And we want to solve that out for t. And when we do, in this case, t is going to end up being 7.87 seconds. So on problem number 12, the correct answer is C, 7.87 seconds. All right, problem number 13 is the same problem, except in this case we're trying to find the range, the horizontal displacement. Now something we need to remember from the previous problem is that the time in the air, the total time in the air, was 7.87 seconds. To calculate the range, we're going to use delta x equals vt. We know that the horizontal component of the velocity is constant throughout a trajectory, assuming that we can ignore air resistance. We did not find previously, though, the value for that horizontal component. So let's draw back in our original vector of 60 meters per second at an angle of 40 degrees above the horizontal and to the right. Let's draw down a 90. And in this case, let's solve for this horizontal component. To do that, we're going to say the cosine of 40 equals adjacent, which is our Vx, over the hypotenuse of 60. And we're going to solve that out. So we're going to say the cosine of 40 times 60. And that's going to give us 46 as Vx. 46.0 meters per second. So now to find our horizontal displacement using delta x equals vt, we're going to say the v is the horizontal velocity, 46, times the time, total time in the air, 7.87 seconds. Multiply that out, and our correct answer for problem number 13 is going to be about 362, and that is 362 meters for delta x. So answer A is the correct answer on problem 13. Alright, on problem 14, we're trying to find the maximum height reached by that same arrow. Remember, we're talking vertically here. So vertically, let's just think about vertical quantities. Vertically, our initial vertical velocity was the vertical component of the 60 meter per second vector, and that was 38.6 meters per second, starting out in the upward direction. Our acceleration is the acceleration due to gravity. Remember, that's negative 9.81. And our final vertical velocity, we're at the maximum height here. Remember, at the max height, the final vertical velocity is 0. So there's several ways we could find this maximum height. But probably the easiest way is to use this equation. So we're going to say v squared equals v0 squared plus 2a delta y in this case. We're going to solve that for delta y. So delta y is going to equal v squared minus v0 squared divided by 2a. So in this case, we're going to end up with v squared, 38.6 squared, and that's meters per second square, minus VO squared. VO was our initial, whoops, so we need to back up on that, guys. Our final vertical velocity is 0. So we're going to say 0 squared minus our initial vertical velocity, which in this case was 38.6 meters per second squared, divided by 2a, which is 2 times the acceleration, negative 9.81. And we're going to solve that out for delta x, or in this case delta y. And when we do, we get delta y equals 75.9 meters. That is the maximum height reached by this arrow. Correct answer on problem 14 is D, 75.9 meters. All right, this next problem, problem 15, is maybe a little tricky. We've got the picture over here on the right. Someone has kicked a football, and you can see it moving across its trajectory. Which of the following correctly ranks the speeds of the ball at the 4 locations? So here we're asking about speed, not velocity, which means just magnitude matters. Doesn't matter in this case if it's going up or down, we're just looking at the magnitude of the speed. So hopefully you realize that at point A the ball is going the fastest. And that's true because we know the horizontal component of the velocity is the same everywhere. But what's different here, this ball just left this person's foot, which means it has a maximum vertical velocity. As it goes up, the velocity is positive, but the acceleration is negative. And that means as it goes up, it's getting slower and slower in terms of speed. Once it gets to point C, its vertical velocity is 0. And then on the way down, it has a negative vertical velocity and a negative acceleration, which means on the way down, it's going to be speeding up. So here's the deal. At point A, the ball is going the fastest. Since point B and D, since those 2 points are at the same height, the ball has the same speed at those 2 locations. So we're going to say A is greater than B, which is the same as D, and they're all greater than C. Since at point C, C only has a horizontal component. The vertical component is 0 at that particular point in time. So our answer, correct answer on problem 15, B. A greater than B, which is equal to D, which are all greater than C. All right, problem C has the same scenario, but this time we want to know which best indicates the direction of the acceleration of the ball at point B. Well, from our last problem, we already talked that there is no horizontal acceleration during a projectile problem, during a trajectory. That the only acceleration is the vertical acceleration, and that acceleration is caused by gravity. Gravity is a force, in this case a net force, that always acts straight down. The acceleration is always in the same direction as the force. So it doesn't matter if we're asking about point A, point B, point C, or point D. In all those cases, the acceleration is straight down. And again, that's because the force of gravity acts straight down. So our correct answer on problem 16 is answer B, straight down. All right, so back to another football question here. So we have a building, and someone has kicked a ball, and the ball has gone up. It's past its peak, and then it ends up hitting the building, something like that. And we want to know if we're calling the ground the frame of reference, the launch point right here. We want to know about the vertical position, the vertical velocity, and the vertical acceleration. And we want to know which one of these choices gives us the correct signs for each of those. Well, we know that when we're talking vertically up, it's positive. So the ball hits at a vertical height higher than the initial vertical height. That means the vertical position is now positive. So this column should be positive because we're at a higher height, higher altitude than we started. Now, when the ball hits the building, the ball has already went up, and now it's on its way back down. Since it's on its way back down, that means that its velocity is negative. So it has a negative velocity. This column should be negative. Also, it doesn't matter if we're talking about at the beginning point, or in here, or in here, or in here. The ball is always accelerating, but it's only accelerating in the downward direction because the net force causing that acceleration is gravity. So regardless of where we're at in this trajectory, the acceleration is always down, which means this column should be negative. So we have a positive position, a negative velocity, and a negative acceleration. So it's looking like our correct answer on problem 17, and I just completely messed that up, on problem 17 is B. And again, we have a positive position, a negative velocity, and a negative acceleration if we're talking about the vertical versions of each of those. All right, so now we're looking at problem 18, another projectile problem. And we want to know if a football is punted at 38 meters per second at a 40-degree angle above the ground and to the right. If the ball leaves the punter's foot at a height of 0.75 meters above the ground, how long does it take the ball to return to the ground? So in this problem, the ball is not returning to the original launch height. It's going to fall past that all the way to the ground. Regardless, we're going to find it much the same way we did in previous problems. We're first going to draw our vector, 38 meters per second, at an angle of 40 degrees above the horizontal and to the right. We're going to draw down a vertical, and we're going to find the vertical component of our velocity. To do that, we're going to use sine, and we're going to say the sine of 40 is equal to opposite Vy over hypotenuse 38. We're going to solve that out for Vy. So we're going to say the sine of 40 times 38. And we end up with a vertical component of velocity of about 24.4. And initially, that's in the upward direction. So we know the time in the air is going to be completely dependent on vertical quantities. So this is going to be our initial vertical velocity. We're going to end up with a vertical displacement of negative 0.750. If the ball simply returned to its original height, its vertical displacement would be 0. But in this case, it's going to fall 0.75 meters beyond that, and that's since it's down, we're going to have negative 0.750. Our acceleration is the acceleration due to gravity. And what we've got to do now is try to solve for time. So there's a couple different ways we could do it, but maybe not the easiest way, but the way we're going to attempt to do this is to, we're going to have to use the quadratic equation to do it. We're going to use the kinematic equation, delta y equals VOT plus 1/2 AT squared, where our our vertical displacement is going to be negative 0.75. And I'm going to leave off units here, guys, just so that it'll be easier to see what's going on. Our VO is going to be our initial vertical velocity, the vertical component of that velocity, which is 24.4 times T plus 1/2 times A, acceleration due to gravity, times T squared. We're going to solve that and make it look a little bit more like a quadratic. So we're going to move the 0.75 over, and we're also going to make it look, like I said, we're going to make it look like a quadratic. So the way I'm going to write this in a quadratic form is I'm going to write it as negative 4.9 T squared plus 24 T equals, or plus 0.75 equals 0. So all I did is move the negative 0.75 over to the right, and then I moved the components of the equation around so that the squared point was first, and then just D, and then the 0.75 that didn't have a T variable at all. Now we're going to use the quadratic equation, which hopefully you guys remember is negative B plus or minus square root of B squared minus 4AC all over 2A. Remembering that B in this case is the 24, A is the negative 4.9, and C is the 0.75. Now when you plug all these variables into the quadratic equation, you end up with two answers. You end up with T equals 5.01 seconds. You also end up with T equals negative 0.0305 seconds. Well, we know we can't have a negative time, so that answer won't work. So our correct answer here has to be 5.01 seconds. So the correct answer, problem 18, answer B, 5.01 seconds, is the time from the time the ball is kicked until it returns to the ground. All right, problem 19 is essentially the same problem. We have to remember from the previous problem that our total time in the air was 5.01 seconds. In this problem, we're looking for the range, the horizontal displacement. And we know that the horizontal displacement, the range, is determined by the initial horizontal component of the velocity, which is always constant. So we need to draw in our original vector, 38 meters per second, traveling at 40 degrees above the horizontal and to the right. Do vector resolution. In this case, we want to solve for the x component, so we'll use cosine, and we'll say cosine of 40 equals adjacent, Vx, over hypotenuse, 38. We're going to solve that out for Vx, so we'll take the cosine of 40, and we'll multiply it by 38, and we'll end up with 29.1 is our Vx. We know that during a projectile problem, that horizontal component doesn't change. So this is a constant velocity. So to calculate our range, our horizontal displacement, we're going to say delta x equals our horizontal velocity, 29.1, times our time, the total time in the air, which in this case is 5.01 seconds. We're going to calculate that out, 29.1 times 5.01, and we end up with a delta x, in this case, of 146 meters. So our correct answer on problem 19 is answer B, 146 meters. Some of you are going to look at problem 20 and say, oh, that's the same thing as problem 17. But what you need to keep in mind is that problem 17 was asking about vertical position, vertical velocity, and vertical acceleration. This problem is looking at the horizontal components of all those same things. So we're throwing softball. Which of the following correctly describes the ball at point B? Assume the red arrow indicates the origin or the frame of reference. So we're starting here. We're talking about horizontal in this case. So at point B, horizontally, we're to the right of where we're started. So that means the horizontal position, and we'll use X because that's typically what we use for position. The horizontal position is positive. The ball is still moving to the right, which means it has a velocity that's also positive. In terms of the acceleration, remember that in a projectile problem there is no horizontal acceleration. So the horizontal acceleration is not gravity. It's not negative 9.81. The horizontal acceleration is 0. So it looks like our correct answer on problem 20, positive position, positive velocity, 0 acceleration, at least horizontally. Correct answer is D on problem 20. All right, so now we're going to look at FRQ practice problem number 1. 4 arrows, A, B, C, and D, were launched from ground level and allowed to return to the level ground. The data table located to the right illustrates the motion of these arrows. So our table is giving us the initial vertical speed, the initial horizontal speed, and the time of flight. First thing we want to know is we want to rank the arrows in terms of horizontal distance traveled, from greatest distance to least distance, and we're going to justify our answer. Well, hopefully you guys remember that during a trajectory, the horizontal speed doesn't change. And the horizontal displacement is calculated using delta x equals vt. So to calculate each of these ranges, for example, for problem A, we would go the speed, 40, times the time, 6. For B, 60 times 4. For C, 50 times 5. And for D, 80 times 4. So when we calculate those out, we end up with this answer. D ended up with the greatest range of 320 meters. C was second with 250 meters displacement. A had 240. That was also equal to B, which also had a range of 240 meters. So now let's move down to part B. Rank the arrows in terms of the magnitudes of their accelerations while in the air, from greatest acceleration to smallest, and justify your answer. Well, remember that in a trajectory, during a projectile problem, the only acceleration is vertical, and that acceleration is caused by gravity. So the acceleration is completely vertical. It doesn't matter how fast the arrow started out. The acceleration for all of these is negative 9.81 meters per second square. So our answer on B, right here, all of the arrows have 0 horizontal acceleration. The only acceleration is the vertical acceleration due to gravity, so they are all the same in terms of acceleration. A equals B equals C equals D. Moving on down to question C. Question C wants us to rank the arrows in terms of the magnitude of their initial resultant speeds from fastest to slowest. Justify your answer. All right, to get the resultant speed, we need to add together the components. So for example, for A, we would take the horizontal speed of 40. We would use the tip-to-tail method of vector addition, and we would now add that to 29.4, which is the vertical component of the speed. We would draw in our resultant from tail of the first vector to tip of the second one. Call that R. And solve for that using Pythagorean theorem. So when we do, we end up for part A with an initial resultant speed of about 49.6 meters per second. We don't need to calculate the angle here because we're only asking about the speed. We repeat that same process for all the other vectors, and this is what we end up with. D has the greatest speed to begin with of 82.4 meters per second, followed by B, 63.1 meters per second, followed by C, 55.7 meters per second, and the slowest one of all is A, 49.6 meters per second. All right, now let's go down and look at D. D wants us to rank the arrows by the maximum vertical height reached from highest to lowest. Well, we know that the vertical height is determined by vertical velocity. We have the initial vertical velocities for each of the arrows. So to calculate their maximum height, we're going to use the kinematic equation, final velocity squared equals initial velocity squared plus 2a delta y. Remembering that at the maximum height, the final velocity squared is 0. We're going to solve that out for delta y. And we end up with this. Now if we plug in these initial velocities and plug in negative 9.81 for our acceleration, the maximum vertical heights that we get for each of the arrows is given down at the bottom. So arrow A goes the highest, 44.1 meters, greater than C, 30.6. B and D go the same height, which is about 19.6 meters apiece. All right, that's it for FRQ practice problem number 1. All right, so now we're looking at the final problem, FRQ practice problem 2. A group of students measured the vertical and horizontal components of the velocity of a baseball as it traveled through a parabolic trajectory. The data is presented in the table to the right. So we have times, and we have the horizontal velocity at each time, and we have the vertical velocity at each time. First of all, we're asked to graph the vertical velocity versus time, find the slope and the y-intercept of the graph, and write an equation that describes the graph from part A. So let's look at those problems first. So after we plot the vertical velocities against time, we end up with a graph that looks like this. We want to make sure that we clearly label each axis. So time on the x, vertical velocity on the right. Notice we get a straight line. Remember, on a velocity versus time graph, slope represents acceleration. So we calculate slope by picking any 2 points on this line and doing change in y over change in x. So in this case, I used these measurements, calculated the slope, and came up with a slope of negative 9.8. That should make sense to you because the acceleration of this arrow during its trajectory should be the acceleration due to gravity, or negative 9.8, negative 9.81. Now we were also asked to find a y-intercept, so we're just going to extend the line up a bit to right about 2.5 or 2.6, negative 2.6 actually, so that's our y-intercept. And to write an equation for this line, we're just going to write the equation in slope-intercept form, which is y equals mx plus b. So in this case, y equals, the slope is m, so our slope was negative 9.8 times x plus b, which in this case is negative 2.6. So that is the equation for our line. So now let's look at part D. On a separate graph, plot the horizontal velocity against time. Write an equation that describes the graph from part D. Is the baseball on its way up or way down between t equals 0.1 and t equals 0.5? Justify that answer. And part G, calculate the resultant velocity of the baseball at each time interval. So let's go to the next slide and take a look at that. So here's our graph of horizontal velocity on the y-axis, plotted against time on the x. This time we get a straight horizontal line. And that is true because the horizontal velocity doesn't change during a projectile problem. That horizontal velocity was 4.22. The slope of our line is therefore 0. There is no slope. The slope of a horizontal line is 0. And the equation for this line is just y is equal to 4.22. So let's continue on and look at the last couple of parts of this. So part F, we want to know, was the baseball on its way up or was it on its way down during this trajectory? And the way to answer that is to look at the vertical velocities. The vertical velocities during the whole time interval were negative. If you have a negative velocity, vertically at least, that is telling you that the ball is going down. So the ball is on its way down. It's already went up, it's peaked, and we're looking at this portion of the graph. The last thing we were asked to do was to find the resultant velocities. To do that, you had to add together the horizontal and vertical components of the velocity. So let's do one of those together. So let's just do at time 0.10 seconds. So to get that answer, we would take our horizontal component, draw that in. The horizontal component was 4.22. The vertical component was negative 3.58. Tip to tail vector addition method here. So we want to add those together using that tip to tail method. So 3.58 down, that's what the negative means. Drawing our resultant from our tail of our first vector to the tip of our second, like so. Use the Pythagorean theorem to solve for r. When we do that, we get 5.53 meters per second. We want to solve for the smallest angle between the horizontal and the resultant, which is that angle. We'll use the tangent function to do that. And when we do, we get 40.3 degrees. And our direction on that is below the horizontal and to the right. So the resultant for the 0.1 second time interval, 5.53 at 40.3 meters or 40.3 degrees below the horizontal and to the right. We'll continue the same process for all the others, using the tip to tail method to add together the horizontal and vertical components. And once we do that, these are the correct answers that you should obtain on Part G. All right, I hope this helps.